Welcome everybody. It's a pleasure to have Doctors Anowar Shajib and Martin Millon here today. Thanks a lot for accepting our invitation. Dr. Anowar Shajib is a fellow at the Kavli Institute of Cosmological Physics at the University of Chicago and was previously an Einstein Fellow at the same institute. He obtained his PhD at the University of California in 2020, working with Tomado Troy. He is an active member of the LSST Dark Energy Science and LSST Strong Lensing Science collaborations. He is also the founder of the AstroBridge program, which facilitates research projects and workshops for undergraduate students across the globe with limited access to such opportunities. Dr. Martin Millon is an SNSF Fellow at ETH Zurich. He obtained his PhD at EPFL, Switzerland in 2021, where he studied strong gravitational lensing, time delay cosmography, and the study of active galactic nuclei through microlensing. He was a member of the Cosmography and Holocaust projects and is an active member of the LSST, Dark Energy Science, and Euclid collaborations. Both speakers are members of the TDCOSMO collaboration. Today, they will talk to us about TDCOSMO 2025, cosmological constraints from strong lensing time delays. Anowar, Martin, please start in your own time. Thank you.
Thanks a lot, Jackson.
Yeah. Thank you.
Thanks a lot for the very nice introduction. So hi, everyone. Thanks a lot for joining this presentation. So today, I, Anwar Shajib and Martin Millon will present these newest results from our collaboration, the TDCOSMO collaboration. So this is our 2025 milestone paper result. And as we will describe in this presentation, this is really a compilation of work from many, many years. So the last big such milestone or compilation was presented in 2020. So a lot of work was done in the last 5 years, but really, there are work dating back to the late 2000s that have allowed, these cosmological results that we're going to present today. There are many collaboration members also in the audience. Big shout out to all the other TD cosmonauts who are in the audience. So the talk today will be divided into two parts. So first, I will give a general introduction to the method that we call time delay cosmography. And then I'll explain the previous results up to this milestone 2025 to set a baseline for Martin Millon then to take over and then tell us about what's newly done in this TDCOSMO 2025 milestone and what are the cosmological results in terms of the Hubble constant measurement and other cosmological parameters that we have. So to start off with the Hubble tension. So for the audience of this CosmoVerse seminar, I don't think Hubble tension is an unfamiliar topic, but just to provide the setting here, this plot may be familiar to many of you, which is showing the tension in the Hubble constant between the two sets of values. So one is coming from the CMB-based measurement, which are the red points, first from the WMAP satellite and then the Planck satellite data. And the other is using the cosmic distance ladder of type 1 as supernova that is calibrated with Cepheid. So the last few points here, most of the last points here are from the SHOES collaboration. And the first point here is from the Hubble Key project shortly after the year 2000. So yeah, as you can see, although after the year 2000, there was an agreement, but as time passed, our data got better, there was tension that arose. And now the tension is more than 5.3 sigma between these two conventional methods of measuring the Hubble constant. Here is another view of this landscape of the Hubble constant measurement. So basically on the top part, here are points, many of them are from CMB-based measurements, not just Planck experiment, but also from ACT and SPT. And the others that are using BAO with some other early universe probe, like the Big Bang nucleosynthesis. So these group of points that depend on, their mechanism depends on early universe physics, as opposed to these other group of points down below, which most of them are using the distance ladder based measurements with several combinations of the calibrator or the distance indicator. So instead of supernova, another distance indicator can be surface brightness fluctuation method. So all of these measurements at the bottom section, so we are calling them the late universe measurement. So you can roughly see there is a dichotomy here between the early universe measurements and the late universe measurement. So which points to a very interesting direction or hint toward what can be causing this tension. So if we can rule out systematics from all of these measurements as the source of this tension or discrepancy, then there is potentially some new physics that needs to explain this tension. So in terms of the theory landscape, what kind of new physics we may want to have, so it would be something beyond the standard cosmological model right now. So possibly some new element like an early dark energy. So for example, the dark energy that we talk about is the late universe dark energy that became a dominant component in the universe, relatively closer to redshift 0. But early dark energy will be a dominant component of dark energy at a very early time, so before the epoch of recombination, which was at a redshift of about 1,000. Or there can be other additional particles that could explain this tension. So this is a very interesting question and an intriguing puzzle. So I believe lots of cosmologists, both theory and observational side, are really looking into this tension. But the key point here to really declare this tension to have a physical origin, we need to exclude the presence of systematics from all of the measurements that we're having. And one of the most effective ways to exclude systematics from one observation is to have another independent observation that doesn't share the same systematics. And if independent observations agree to a good level of precision, then that's a very good indication that there is no systematics in them, and we are looking at some very interesting new discovery here. So on that point, our method of time delay cosmography is a completely independent method of measuring the late universe Hubble constant. So before explaining how this method works, let me just give you a few of the advantages of this method. So this is a one-step measurement of the Hubble constant, as opposed to having to use multiple steps, like in the cosmic distance ladder measurement. So there is less risk of systematics hidden because there is just one step. The physics is well understood, so gravitational lensing is explained by a very well-tested theory of general relativity. And the measurement is based on distance measurement that is an angular diameter distance, so that is not vulnerable to dust extinction like luminosity distances can be. So the main phenomena that we are using here in our method is strong gravitational lensing. So let me just show you a video first for what strong gravitational lensing can be that you can observe right on the Earth. So here you can see in this aquarium, and the fish swims behind the corner of the aquarium, light coming out of the, reflected off of the fish is refracting around the corner in such a way that you can see multiple images of the same background fish. Now, a similar phenomenon also happens in space. So when there is a very distant quasar and the light emitting out of the quasar goes past an intervening galaxy, then due to the gravitational effect of this intervening galaxy, it bends around and then arrives us in a way, so we see multiple images of the same background quasar. So now when this happens, there is a time delay of the arrival time of the photons that were emitted at the same time from this background quasar. So there's two effects that creates this time delay. So one is geometric. So you can see from this schematic that there can be a path difference in the path traveled by the photon. So that creates a time delay in their arrival time. And there is also another additional delay caused by the gravitational potential, because these two photons may have gone through different depths of the potential well created by the lensing galaxy in the middle. So the geometric component of the time delay, which depends on the difference between the path distances. So these are cosmological distances. So that's why if we measure this time delay, it carries information about the cosmological distances involved in this scenario. And that in turn gives us information on the cosmological parameters, primarily the Hubble constant. So to make this measurement happen, we need 4 ingredients in total. So here I'm showing you an equation just to illustrate how different pieces of data sets or ingredients come together to give us a measurement of the Hubble constant. So the first part of this equation in the red box here are coming from these 4 pieces of data. So first, the time delay information. So this is what we measure by monitoring the quasar from by getting a light curve of the different quasar images, like the one shown here. Next is the pharma potential difference term. So this potential difference is created by the mass distribution of the lens in galaxies. So we model that mass distribution from a high resolution imaging, like this one shown here. Next is an estimate of how much perturbation is being caused by all of the line of sight structures like galaxies and clusters and groups, etc. So they may also have a perturbation in terms of the lensing effects up to a few %. And that is important to correct for because we are doing precision cosmology here. And then the last part is this lambda int term, which I'll explain later in more detail, but we constrain this term using stellar kinematics obtained from spectra of the lensing galaxy and do dynamical modeling with that. And this last part here is a function of redshifts and several other cosmological parameters, except for Hubble constant. And that is because we are measuring distances up to the redshift of the lens galaxy and the source galaxy, which are these Z sub D and Z sub S terms. And so, so there is a dependency on the expansion history up to those redshifts, which depend on these other cosmological parameters like omega m, omega k, given if these parameters are allowed to be free in a given choice of cosmology. So from this term is where we get sensitivity to this additional cosmological parameter, which Martin will later show you the results on these terms. The dependency on these terms is weak, and it doesn't strongly alter or impact the value of the Hubble constant. But it is helpful to have some prior on these additional terms, cosmological parameters. So, for example, we have used additional priors from external data sets like the supernova or BO that Martin will show you later. Instead of using a cosmological model, we could also use supernova relative distances to bridge together the relative expansion history up to the relevant redshifts here. And we have found that that alternative method also doesn't change or alter our main result on the Hubble constant. So a few more details on these data sets and what we do in terms of gathering the data and analyzing them. So first, the time delays part. So here is a video that shows you the monitored data points that is measuring the magnitude of all of the 4 quasar images that you show here. So quasars are intrinsically variable. So that's why by looking at the light curves and how delayed or lagged these light curves are related to each other, that allows us to measure this time delay. So that's what we need to measure this time delay, like a variable background source. So when this time delay method was initially proposed, it was initially proposed for supernova. But until recently, lensed quasars, strongly lensed quasars, were more commonly found than lensed supernova. So that's why right now our TDCOSMO collaboration is measuring time delays and cosmological parameters from lensed quasars primarily. But only recently we have started to discover lensed supernova as well. So that's another exciting avenue to measure or to do time delay cosmography with in the future. So next is the lens modeling aspect. So for lens modeling, what you need is high resolution imaging. So mainly we have used HST, Hubble Space Telescope imaging in multiple bands in most cases. But we have also used imaging from ground-based telescopes with AO assistance, like from the Keck telescope. And more recently, we have also used JWST imaging. And in all cases, we have found that given the quality of the data is high and the resolution is high, these different imaging data are in very good agreement. But here, how it works in terms of modeling the image. So given this Hubble Space Telescope imaging of this system, and you see the color image here because there are three different filters combined to create this RGB image here. So given this image, we want to recreate what that data looks like. So basically, we want to have a predictive model. In our model, we have a description of how the mass and light is distributed in the central lensing galaxy here. And then we have a description for how the flux of the background galaxy, that is the host of the quasar, is distributed here. And then we also need an estimate of the point spread function, PSF, but we also improve that PSF by iterative reconstruction as simultaneously during the modeling. And then the quasars are modeled as a point source that is being depicted as the star here. Now, given these model components, we ray trace the light coming out of this background galaxy and then lens it through the potential field of the lensing mass distribution to recreate how the arc and the quasar image would appear in this imaging. So this is a model-based reconstruction that has been optimized. So basically, then that creates us a way to compute the likelihood function. And then we sample the posterior of all the model parameters using MCMC techniques. So here is another presentation of how well we can do this. So this is another system which has three-band, three-filter imaging from the Hubble Space Telescope. So this first column is the data. The second column is the model-based reconstruction. And this is the normalized residual. So the residual divided over the noise levels. And you can see the modeling has been done to the noise level of the pixels. In terms of what kind of mass model we use, so there are two types of mass model we have used in describing the mass distribution in the lensing galaxy. So the first is a simple power law mass model where this is showing you the projected mass density versus the radius. And another model, which is more physically motivated, is an NFW for the dark matter component and a mass follows light, or basically the stellar light profile to give us the shape of the stellar mass distribution. Then the combination of the two gives us a total mass profile. So this is what we call the composite model. So given these two different mass model descriptions, we have found that they agree very well to each other. So this is a plot from Martin's paper in 2020. So this is the TDCOSMO 1 paper, where this is showing the combined Hubble constant measurement from 7 lensing systems here, from the power law, and this is from the composite model, which are in very good agreement. The next part is the estimation of the line of sight perturbation, which we denote with this kappa x term. So to get this estimate of the total perturbation being caused by all of the line of sight structures, galaxies, group, or if there are nearby clusters present, we've compute a summary statistic of the lens environment. So this plot is showing you a 4 Archimedes by 4 Archimedes view of the lens environment, where the lens is positioned at the center, and all the squares are showing you the other galaxies along the line of sight. And so from this kind of photometric data of the lens environment, the summary statistics that we count, we estimate, we take is a galaxy count weighted with several several types of weighting, and then that summary statistic is compared with fields from Millennium simulation. And in the Millennium simulation, we can compute the perturbation that is being caused by all of these line of sight structures. So by comparing the summary statistic from our observed field to the simulated fields in the Millennium simulation, we have an inference or estimate of how much that line of sight perturbation can be. So we get a distribution of the possible perturbation. So in that way, we have a measurement with uncertainty on this perturbation effect. So this is our main way to measure this external convergence term, or the line of sight perturbation. But we have also tested this measurement with another method that uses weak lensing information around the field in the field of the lensing galaxy. And we have found that this alternative method to measure this perturbation agrees very well to our main method of using galaxy counts. So here is an illustration of the impact of this correction. So in this plot here is the Hubble constant measurement from each, from individually from 7 lens quasar systems before making the correction. And you can see there is then a correlation that with this kappa external term, where if it's below 0, then that means it's a relatively underdense environment. And if it's over 0, then it's an overdense environment. But if you make the correction for the measured or estimated kappa x, then this correlation goes away. So note that we are not correcting here for the correlation we see here. These corrections are already made with measurements that is done previously, and then this correlation just disappears. The last term here is the lambda nth term. So that comes from this mass sheet degeneracy that is existent in lensing. So, and this degeneracy stems from this mathematical transformation called mass sheet transformation, which is being shown by this equation. So quite simply, if we start with a given mass profile that describes our data very well or fits to the data, and let's start with the power law mass distribution here. So given that mass distribution, we can transform that mass distribution using this equation with this lambda factor. And then the second term here is adding a sort of sheet of mass that has a constant amplitude with a factor of 1 minus lambda in front. Then this transformed mass profile, this kappa lambda, the nature of this transformation is such that this transformed mass profile will describe or fit to our observed lensing data, the imaging data, equally well. But unfortunately, these changes the prediction for the time delay. So when we compare the predicted time delay from the model versus the observed one, that then alters the inference on our Hubble constant. So basically, it's a linear dependency on this lambda term. So we can break this degeneracy with non-lensing data that is not vulnerable to the same degeneracy. So stellar kinematics, as I will show you more in a few slides later, that can break this mass sheet degeneracy. So one way to understand what can physically be happening that can cause this mass sheet degeneracy is being shown in this figure. So the red line here is a power law model. So this is a log-log plot of projected mass density versus radius. So the power law model is a straight line, like the red line here. Now, if we think about a core dark matter profile, which is being shown with this black line, that has a very large core radius up to around here. Now, if we have some non-negligible amplitude of this core dark matter, and we can adjust that amplitude by using this lambda parameter. So for a lambda value of 0.9, then this power law mass profile can be transformed through this equation to this green line, where you can see the core is appearing a bit, and it also changes the slope of the mass profile by some amount. And as you make the core larger and larger, there is more and more deviation from the initial power law mass profile. Now, so the degeneracy is that the lensing or imaging observables that we do our mass modeling with is degenerate with these kind of changes in the mass profile description, and that can alter the Hubble constant. So the initial way we have measured this Hubble constant, so going back to the results from Holy Cow and TDCOSMO 1 papers, there we have assume this lambda int parameter to be 1, which means that when we assume the mass profile distribution is parallel, there is no more deviation beyond that. And there is good reasons for us to make that assumption to describe the mass profile in these galaxies using a parallel. So if we look at larger sample of lensing systems, so using galaxy-galaxy lensing systems from the SLACS sample, and combining their stellar kinematic information to break the mass degeneracy with the lensing information, we have found that the parallel mass profile on average is a very good description for the total mass distribution here. So in this plot, this is the dark matter distribution in dark. Blue is the stellar mass, and the total mass profile is the purple band. This is showing you the average deviation of the mass profile distribution in this sample of SLACS galaxies. And on average, the parallel distribution matches with what we find within 5% precision. And not only lensing, but also just dynamics-only modeling using resolved kinematics of local elliptical galaxies. Other observation that uses X-ray to estimate the shape of the potential, and also in hydrodynamical simulations of galaxies, like all point to the parallel model to be a good description of the mass distribution in the massive elliptic galaxies. So we do not know if that parallel description holds to the high level of precision that we are trying to measure Hubble constant here. So that would be a 1% precision goal that we set for ourselves. But assuming this parallel mass profile holds, and as I've just shown that this is a justified assumption, so these are the results based on this assumption. The first from Holy Cow that presented this 73.3 plus minus 1.8 kilometer per second per megaparsec measurement, which is a 2% measurement of the Hubble constant, and agrees very well with the local distance, the local measurement using the cosmic distance letter from the SHOES team. TDCOSMO 1 extended the Holy Cow sample by adding one more lens and finds the same result. So now these results we are calling the assertive model assumption because we are assuming lambda int equals to 1, and so we are using primarily the parallel mass model here. Although there is cross checks with NFW plus STERS model. One important point here is that all of these lenses here, so 6 and 7 in these two results, all but one were analyzed blindly. So to avoid any experimental bias in the measurement being done here. Now going forward, in TDCOSMO 4 paper that came out in 2020, we redesigned our experiment to allow lambda int parameter to be freely variable. Because as I mentioned a couple slides ago, that we do not know if the parallel mass model assumption holds up to the very high level of precision that we want to measure our Hubble constant. So that would be a 1% precision goal. And so, so we do not want to underestimate the errors that are solely coming from the data. So here in this redesigned experiment, we allowed lambda int parameter to be free, so allowing deviation from the parallel mass model. But then we constrain this additional degree of freedom using stellar kinematics that breaks the mass shift degeneracy. So here is the result of the TDCOSMO 4. So allowing that additional degree of freedom then naturally inflates the errors. So now we have about 8% error from the sample of 7 time delay lenses that was analyzed in TDCOSMO 4. Also in the paper, we have added additional lensing plus dynamics information from a sample of non-time delay lenses. So these are galaxy-galaxy lenses in the SLACS sample. And because it doesn't have a variable source, we cannot measure time delay in those lenses to do time delay cosmography directly, but their lensing and kinematics information can still provide us a prior information on the mass profile distribution, which we added here in the TDCOSMO 4 paper, giving us this value of 67.4 plus minus 5%. So, the additional information decreased the error from 8% to 5%, but it also shifted the value here. But more recently, we found out that the spectroscopic data that was used that came from the original SDSS survey had suboptimal signal-to-noise ratio. So basically, there is an additional 6% systematic error that we found that was not added in this initial or this in this result when it was reported. So this is reported in our recent paper from Cannibal et al. 2025 that this signal-to-noise ratio is insufficient for precision cosmology. So we do not recommend for this value to be used anymore for that reason. So that's all from me. Next I'll give the mic to Martin.
Yes, and now we'll present what is new in this TDCOSMO 2025 analysis. We'll list like the different things that we've changed. We mostly improved our treatment of the kinematics, but we also added this 8th system, so VGD 2038. You see the light curve here. This quasar is not very variable, so it doesn't have very precise time delay estimate, but still it gives an additional constraint on H naught when added to the sample. So the results were presented for the single lens in this paper, if you want to have a look too. The second change that we made was introducing a new improved method for our measurement of the stellar kinematics. So as Anowar said, when you relax this lambda parameter, you rely more on the data and less on the model. So it becomes very important to measure the velocity dispersion of your lens galaxy accurately. And this has been investigated by Sean Knabel in this paper. And the main takeaway message is that you can have 1% accurate measurement of the velocity dispersion if you have a sufficient signal-to-noise ratio in your spectra. Here you see the difference between the SDSS spectra, which is much more noisy compared to the KCWO data that we are now using, that have a much higher signal-to-noise. You need also like clean spectral libraries. We need to remove like the stars in your stellar libraries that are affected by some artifacts. And provided that you can marginalize over several like spectral libraries, you could reach this goal of 1% accuracy, given that you have good data. So we adopted this method from the TDCOSMO 19 paper and reanalyzed all our time delay lenses and non-time delay lenses with this method. Second thing that we've changed is we added like better kinematic data, new spectroscopic data, either from MUSE. Here you see two systems observed by MUSE. So you see like the really nice absorption line from the Kelcham H and K lines. And the width of the line will give you an estimate of the velocity dispersion. We've done the same thing for another 5 systems with the near spec data. And now since this is an infrared observation, you use the calcium triplet to perform your velocity dispersion measurement. So, and for one lens, we've used the near spec result spectra. So this is the IFU data that you can get from near spec. So every pixel here is a spectra. So you could basically have a resolved velocity field, and you can perform this measurement, like measuring the width of the line in some analy around your lens. So here you see the different fit in the different analyte from the IFU data. And here you see the velocity profile as a function of radius from the center of the galaxy. So we've measured this with 6 bins. So it gives you a second constraint on the shape of your mass profile in your lens galaxy that complements the lensing data. Here you see the same lens, so the velocity dispersion profile observed by JWST near specs in comparison with Keck. So the two are different, but it's expected because JWST has a much narrower PSF. Here you've got some smoothing due to the observation taken from the ground with the Keck telescope. But the model, that the fit to those data agrees pretty well. As you can see on this plot, so this is a single fit to this lens, Eric J 1131. And you can see that using the KCWI data or the JWST data gives you the same power law and the same lambda int for this lens. If you combine the two, you get a more precise measurement. And if you add the lensing prior, because lensing is also measuring the slope of your profile, you get an even narrower distribution for gamma, which is the slope of your mass profile. So this is something what we've changed. We've included this resolved velocity dispersion measurements for 1131 to constrain our mass models. The other thing that we've done is a better selection for the external dataset. So there is the SLACs and the SL2S sample of lenses, which are non-time delay lenses, but they are galaxy-galaxy lenses. So they don't have a time delay, they don't constrain H0, but they help constraining the mass distribution of your galaxies. And to make sure that there's no selection effect between the two samples, we make sure that the SLACs and the TDCOSMO sample are similar. So we have a bunch of cuts that we place to ensure this is the case. You see here, like, I mean, it doesn't really matter what all these quantities are, but the point is that like the distribution of the time delay lenses and the non-time delay lenses match pretty well in all these dimensions. We have also included a correction. So this is a statistical correction for a departure from sphericity in our kinematic modeling. So we do that statistically at the sample level. You can see it's dependent on the ellipticity of your deflector, but most of our deflectors are above 0.8 here in ellipticity. So it means that the correction is actually very small. It's like a 1 to 2% correction that we apply to compensate from our spherical modeling to account for the fact that like an axis symmetric modeling could be more representative of our data. And we have also homogenized our treatment of the line of sight effects, both for the TDCOSMO sample and for the external sample of lenses. So now I will show the results. So this is our baseline measurement of the Hubble constant, 72.1 plus 4 minus 3.7. This is in combination with the Pantheon Plus datasets. So the Pantheon Plus supernovae dataset not anchored on SHU, so it constrained mostly omega m. So it's effectively using the Pantheon prior on omega m. This is our baseline measurement, and if you add the SLAC and the SL2S sample, so an external sample of lenses, you get a slightly more precise value, but it is in very good agreement with the baseline value that uses only the 8 time delay lenses. We've also tried to use the DESI BO DR2 data in our analysis. This is basically constraining omega m. We're not using a prior on RD. So RD, the sun horizon scale is left as a free parameter in this fit. So it's the unanchored BAO distance, if you want. And this gives you our most precise estimate of the Hubble constant of 73.0 plus minus 3 kilometer per second per megaparsec. And if you want to compare with the previous measurement from the Holico and TDCOSMO 1, we've also run the fit with the same prior, the same flat omega m prior, and this gives you this value and this value. So most of the shift here is explained by the choice of prior on omega m, so the choice of the expansion history. The standard lensing is measuring mostly the expansion rate of the universe today, but it has no very weak constraint of the expansion history of the universe. So here is the main corner plot. Here you've got H0, omega m, which is mostly constrained by the Pantheon Plus data. And our measurement of lambda int, of this deviation from Apollo, it's fully consistent with 1, meaning no deviation from Apollo. And this is consistent across the 3 lensing datasets. So now I will just present the results in some extension of the lambda CDM model. This is using a free omega k. And you find out that using TDCOSMO only basically don't constrain omega k. You really have a not much constraining power on the expansion history. But if you combine with Planck, there is a slight tension between the two datasets, like just below 2 sigma, but you can still safely combine. And you still find it basically shift the Planck value for the curvature towards 0. It gives you this value of the curvature compatible with no curvature. And and you can see that using TDCOSMO only, you still have a fairly well constrained Hubble parameter of 74.2. In WCDM cosmology, where you leave the dark energy equation of state parameter to be free, you also constrain H0 pretty well, but you're not really constraining W with TDCOSMO only. It's only when you combine with Planck or the BAO that you start constraining these parameters and H0 at the same time. And combining with BAO, you find no evidence for a deviation from a cosmological constant. W is compatible with -1. It's combining with Planck, you see a slight deviation, but it's also pushing the Planck value toward -1, which is a cosmological constant. In another extension of the lambda CDM model, using the W0, WA parameterization, you find also a pretty well constrained Hubble constant of 72.0. So it's pretty stable across all assumption for the cosmological model. And you see that combining TDCOSMO plus the BAO plus the Pantheon plus datasets, you find basically no deviation from cosmological constants. So WA equals 0 and W0 equal -1. It's only when you combine with Planck that you could see some evidence for evolving dark energy. Here again, the main what time delay cosmography is adding to this measurement is the constraining of the Hubble constant. So here is just a summarizing plot of the Hubble tension, like giving the main measurement that has been published in 2024 and 2025. The TDCOSMO measurement slide and it's a late probe of the Hubble constant, and it finds like a rather high value compared to the early measurement from Planck, ACT, or DZ-DR2 using DBN. What are the next steps for our collaboration? First, it's to improve the statistics. We are currently modeling many new lens quasars that will be added in a future release. We also have like time delay measurements for a large number of lens quasars. Now there's 22 that has been published recently in this paper. And we are also measuring them much faster than before, given these very high quality light curves that we are now obtaining. The next step would be also to divide our sample. When we get a bigger sample of time delay lenses, we could start making some comparison, for example, between the double and the quad that might be affected by different systematics, because the potential is probed at different distance, so you might start seeing different systematic. And as we go, we're still assessing the impact of various systematics. So there is a lot of them listed in the paper about the mass modeling assumptions, selection effects, peculiar velocity, dark matter substructure, that all of those are, we think that they are below a sub%. They have a sub% effect on our measurement of the Hubble constant for now. But as the precision increases, we might start accounting for those small effects. And what's coming next is also the JWST near-cloud modeling that now fully agrees with the HST modeling for the single lens that we have analyzed so far. And we will have like a full TD kinematic modeling of the 6 lenses that have been observed with near-cloud. That will also provide more constraint on the shape of the mass profile of those galaxies. And we're also planning to use some exotic lenses. For example, this is one that has been discovered recently with a first deflector at redshift 0.18, a second deflector at redshift 1.88, and the quasar multiplied 6 times at redshift 2.38. And we thought originally was a dual AGN being lensed 2 times and 4 times. It's actually a single quasar lensed 6 times because there's 2 optical paths doing a zigzag between the 2 deflectors forward. So this system is very interesting because it's 2 cosmological probes in one. First, you've got 2 Einstein radii that you can measure at 2 different redshifts. And this probes like the ratio of distances, and it's basically give you a measurement of the expansion history of the universe. It doesn't measure H0, but the history of the expansion of the universe. So it's sensitive to W. And you also have like 5 independent time delay in the system that give you a measurement of H0, so the expansion rate the universe today. And this system also provides additional constraint on the internal massive degeneracy parameter, lambda, without the use of kinematics. So just to conclude very briefly, we've now integrated like a lot of new data from KCWI, MUSE, and JWST to relax our previous assumption about the mass profile of the galaxy. We have developed a new methodology that guarantees sub-percent systematic error on the kinematic measurements. And we obtained H0 measurement at 4% precision in a very good agreement with the shoes value and in slight tension with the CMB value. And the future milestone, we include more system, new NIRCam and new spec data, and the full 2D modeling of the velocity fields of our deflectors. So I will stop here and we will take some questions. Thank you.
So thanks so much. Fantastic talk and amazing results. So any comments, questions from the audience? I don't see. Meet?
Yeah, thank you for the wonderful talk. My question is, when you showed the omega k and the Hubble H0 values for the TDCOSMO and the TDCOSMO plus Planck, those were very different. So is there a way forward in the future that you will also consider other data probes, such as, let's say, Pantheon Plus or anything else for fitting, so that you would have a good probe across all parameters that are there, or it's just going to be comparison with the Planck? Because H0 value of 76 and 67, if I read it correctly, that's very different.
Yeah. So it's basically the Planck value in open lambda CDM cosmology is around 55. So the combination with TDCOSMO bring it up to 65. I think there is nothing really new here. It's like Planck is in this slight tension with the lambda with the flat curvature. We are just adding the measurement of the Hubble constant, but it's also another aspect of the Hubble tension, I would say, that you see here. And I don't think if you add the Pantheon data, basically, it's not constraining H0 on itself. It's just if you add the shoes value, that you will constrain H0, and you will probably get the same similar results in this parameter space.
Okay, got it. And any other ideas for like the DESI results or the ACT results to be included for this, or is just the characteristic nature of the Hubble tension that if we take the Planck data set, then it shifts to 65 along with TDCOSMO?
Yes, like it's a 2 sigma tension, so we still combine, but that's probably hinting at something maybe a bit fishy here. But I didn't understand the first data set that you mentioned.
So the dark energy spectroscopic instrument data release to the
DESI data. We didn't combine in open lambda CDM, but we did it in other cosmology, and it's fully consistent with DESI, as long as you're not using the RD prior from the CMB or from Big Bang nucleosynthesis. If you let the sound horizon free, you could basically anchor the BAO distance onto the time delay distance, and that gives you something fully consistent, as you see here.
Okay.
But if you would use a prior on RD from the CMB, you would also see the tensions.
Got it. Thank you so much.
I think Maurice has a question.
Yeah, thanks. It's a pretty basic question. In the setup of the basis of your measurement includes a lambda that is essentially a modeling parameter, I understand. So what part of the uncertainty of 4 kilometers per megaparsec is actually due to the uncertainty in lambda? Can you comment on that?
So maybe I can take that question. So if we fix lambda parameter to 1, then we have a little below 2% error. So although we haven't directly estimated like what's the uncertainty budget directly from lambda, but we can make a rough estimate that it's the final uncertainty. So plus minus 4 is 5% here. If we have fixed lambda, then it would be like a little below 2%. So the lambda is providing 5% minus 2%, but in squared terms, if that makes sense. So right now, that's the major source of the uncertainty in the final measurement.
Thanks. Will that go down if you have a larger sample, or will the lambda uncertainty remain?
So it would go down only with stellar kinematics data, because that's the data set that is sensitive or to constrained lambda. But with larger sample of lenses, it would unfortunately not go down. But well, a larger sample of lenses with only lensing information or imaging information, it will not go down. But if we have more kinematics data, then it will.
Hi, close to the beginning. Thanks for the talk. It's very informative. Close to the beginning, Anwar showed an equation. Would it be possible to go back to that slide? It's an equation that there is an if. Well, you say that it's quite, yeah, this one. So, so this is how you calculate H naught, and that function depends on parameters of an assumed cosmological model. Is that right? And then
Right.
you did say that there's an alternative way of calculating it that's independent of a cosmological model. Is there any
Right.
reason why you wouldn't just use that alternative way, that's more independent?
So the alternative way would be using supernova data set. So that's a data dependent way instead of being model dependent. But to explain what this F function is a little more, so basically this is if you take the formula for cosmological distance, and if you take out the H naught, the remaining part is that gives the some sort of normalized distance except for H naught. So here, this is a ratio of those distances up to the ZS, and in between the lens and the source. So that'd be Z. The distance between those two redshifts. So basically, because these are still distances, if you use relative expansion history coming from data like supernova or BAO, that would be an alternative way. So, but there is no practical difference here to just use the data set. So there is no clear indication that solely using the data here instead of assuming a model is a better choice. As I've said here, that both ways give us roughly the same answer.
So you're not also using this method to constrain the matter density fractions? So you're inputting the density fractions in, like you're fixing it, or are you constraining it?
So it's very weakly constrained by time delay cosmography alone. The data point where we use the flat prior for omega m between 0.05 and 0.5 is it's these two here at the bottom. So omega m is basically unconstrained. It has just a slight degeneracy of H naught. So if you change the prior on omega m, it's slightly less precise if you take a flat prior compared to these datasets which use a prior from Pan plus, but you still constrain H naught. So that's both the advantage and the disadvantage of this technique is like it's mostly sensitive to H naught and very weakly sensitive to other cosmological parameters.
Yeah, because it feels
So
like you're fixing a cosmology, basically, if you don't, I don't know, maybe I have to read more, but it
So
seems.
to measure cosmological parameters, in addition to H naught, then those parameters need to be embedded in a cosmological model anyway. So in that, from that point of view, it's not a disadvantage of assuming a cosmology. When we are just measuring H0, then it doesn't matter mostly, right? So now, although the current sample size is not large enough to have strong constraint or competitive constraints is omega m and these other cosmological parameters, but our forecast shows that in the future with larger sample, we will be independently,
Understand.
yeah.
I see. So in the future, this technique can be used to test other cosmologies as well.
Yes,
Maybe
exactly.
with a different metric or
Yeah.
okay,
So
cool.
you will need hundreds of lenses to constrain W0, WA from time delay cosmography alone. That's the forecast.
That's
Yeah.
dark energy. But if you assume, I don't know, I'm just saying, like, what if the metric is not FLRW? Do you know what I mean?
Well,
Yeah, so that remains to be tested. So if there are like, extension of FLW metric, and that can be tested by looking at the expansion history when we have that large of a sample in the future. And so we will have those, although 100 seems to be a very large number compared to the 8 that we have now.
Okay,
But
cool.
next 10
Yeah, understand.
Yeah.
Yeah.
But in the next 10
Okay.
years, given Rubin LSST and Roman and other Euclid, so we are hopefully going to be there in about 10 years.
Okay. Thanks.
I think Daniel had a question.
Yes, sure. Can you hear me all right?
Yeah.
Great. Yeah, thank you so much for the talk. It's great. Yeah, it's awesome to see how the field has evolved. I wanted to ask. I have a very predictable question because it's something I was working on. But do you take into account this foreground term that affects your velocity dispersion constraints? So probably you're familiar with this, but when you constrain the mass and the internal mass sheet degeneracy, there's a slight bias introduced by the foreground convergence. Is this something you take into account in this analysis? It's sub%, so it's not dominant, but yeah.
So just quickly, no, we don't. But because as you say, it's sub% at this level.
Sure.
So when we have larger sample size, and as Martin has mentioned, that as our precision goes better and better, we also need to start accounting for these additional effects. But right now, we are not dividing the foreground versus the background contributions to the external convergence.
Okay, yeah. The good news, I guess, is it would be pretty easy to account for just a small additional uncertainty on the lambda. But okay, thank you. Yeah.
Yeah. Thank you for your work to show us that.
Sure.
Yeah.
Thank you. Yeah.
I'd like to thank both speakers again. Thank you very much for your time and for this really nice presentation. Yeah, that's it. So thanks so much again. I'll end the meeting here.